Problem 19, a series RLC circuit has resistance R equals 50 ohms, inductance equals 0.5 Henry, and then we're asked to find the circuit's capacitance C. We want the capacitance if the voltage source operates at a frequency of 60 hertz. So, that was weird. So we have 60 hertz. Okay. Oh, it's frequency of 60 hertz and the impedance is equal to the resistance, and those are both equal to 50 ohms. And then that's part A, right? These are for part A. And then it says for part B, what is the phase angle between the current and the voltage? So we want the phase angle between current and voltage. Okay, so we're given a pretty huge clue right in the problem, right? We're given values for R and Z, so we need to use our impedance formula. So Z is equal to the square root, or let's just write it this way. Z squared is equal to R squared plus XL minus XC all squared. And then so we start to solve, but we want to break these apart first, right? We have identities for both of these, 2 pi times F times the inductance. Are we given inductance? We are, so we can just plug that right in. And since we have a frequency here, 60 hertz, we can use this one as well, 2 pi FC. And we want to solve for C. So what does this give us? Z squared plus, minus R squared equals 2 pi FL minus 1 over 2 pi FC all squared. Well, guess what? Z was equal to R, right? Z equals R equals 50 ohms. So this side is equal to 0. So now we have 0 equals this whole thing squared, so we can take the square root of both sides. That's still equal to 0. So now we have 0 equals XL minus XC, which means that we have XL is equal to XC, which means that we have 2 pi FC is equal to 1 over 2 pi FC. Sorry, this is L. 2 pi FL is equal to 1 over 2 pi FC, right? So that simplifies things quite a lot. So I just kind of took this and plugged that in there in case that wasn't clear. Okay, so just a tiny bit of algebra, and then you're at a point where you can solve for C. Even more algebra. So we have C is equal to 1 over 2 pi F squared 1 over L. And then that's it. And then we just plug in frequency. Here is 60 hertz. 2 pi times 60 hertz squared. And then Henry was, how many Henrys we got? Half a Henry. 0.5 Henrys. So that gives us a value of, wow, okay, so it's 0.00001407. Otherwise, we can call this 14.07 microfarads. That's C. Cool, so next part of the problem we have, find the phase angle between the current, find the phase angle between the current and the voltage. Part B, we want the phase angle. We're given a formula in, let's see, what is it? Number 21.15 in the summary, where tangent of theta, which is the, or phi, tangent phi of the, is the phase angle, is equal to XL minus XC all over R. So then we just take the inverse tangent, XL minus XC all over R. We just plug in what we have. 2 pi FL minus 1 over 2 pi f c r. Let's plug, oh, yeah, so we have values for all these. We have f, we have L, C, and R. Plug that in. So I got a value of close to negative, let's see, what is this? 0.031 degrees. Definitely double check that. That's degrees. In radians it was much smaller. So really, essentially it's 0 degrees. So it doesn't lag with our given conditions. Anyway, next problem, number 24. An AC source operating at 60 Hertz, as usual, with a maximum voltage of 170, also very standard, is connected in series with a resistor R equals 1.2 kilo ohms and an inductor of 2.8 Henry. Part A asks, what are the maximum values of the potential difference across the resistor and the inductor? No, sorry, that was part B. Part A does not ask that. It asks, maximum value of the current in the circuit, I max. B asks for V max across both VR. So you have to calculate V max for both the inductor and the resistor. So that's what we want for part B. Part C, when the current's at a maximum, what are the magnitudes of the potential differences across the resistor, the inductor, and the AC source? So we hold I max, and then we find VR max, VL max, and the AC source, and the V source max. Okay, and then part D, when the current is 0, what are the magnitudes of the potential difference across the resistor, the inductor, and the AC source? So if current equals 0, we want to find all of this again. First thing we're going to do is find I max. Let's look at what we have in the circuit. We have an inductor, a resistor, and then we're told to find the I max, so that's good. So all we have, we don't need to consider XC. We don't need reactance of capacitance. So we can use this formula, 2 pi FL, because we have all of these values, right? 60, 2.8 Henry. So what I'm going to do is I'm going to plug in to our formula that we know for impedance. And because we don't have a capacitor, we don't have a reactance to the capacitance. Okay, so that means that C squared is equal to, what was it? It was 1.2 kilo ohms squared plus XL, which was, if we calculate this, 2 times pi times, what was it, 60 hertz times 2.8 Henry, that gives us a value of 1.1 times 10 to the 3 ohms. Okay, so then we have 1.1 kilo ohms. And so if we just take the square root of all this, here actually we'll have a value for Z. So what does that equal? That equals 1.6 kilo ohms. Okay. How does this help us? Well, we have a formula. I max times Z is equal to delta V maximum. Remember that? We're given this value, so great. We can do I max is equal to V max, and sorry for the sloppy handwriting, my hand's a little shaky. So over Z, that's going to be 170 volts over Z was 1.6 kilo ohms. Just be careful of your units. I'm not writing it out explicitly like I normally do. So this would be 10 to the 3, right? 1.6 times 10 to the 3. So if we plug that in, we get 0.11 amps. That's what I got. All right? That's part A. So all of that was for part A. So what I did was I just used inductive reactance, I plugged it in, got a value, and then I plugged that into the impedance. Found a value for impedance, and I plugged that into our formula here, and solved for I max, which is what we were after. Part B. Next we want the maximum potential difference. We want Vmax and Rmax. Sorry, we want VR max for the resistor, we want Vmax for the inductor. So this is what we're going to do. We're going to use our standard for, let's call this R max for the resistor. And for a resistor, we can pretty much just use Ohm's law, and we have this standard relationship where this is 1.2 kilo ohms times 0.11 amps. This gives us a value of 130 volts. That's the maximum voltage in the resistor. Now for the inductor, it's a little bit of a different, very similar, but it's a little different. We can take I max as usual, and then we multiply it times XL, which is the inductive reactance. Right? This is in the summary of the chapter. I mean, they also explain it in the book if you go back. If you have questions about it, you can email me. 1.1 kilo ohms, which is what we found for inductive reactance, times the current. And this is 120 volts. That's the maximum voltage in the inductor. Okay. Okay, for part C, it says we're keeping the current at maximum. And then we want to know what is the potential difference in the resistor, in the inductor, and of the source. So for part C, we need to know that when we have, let's say, our I is at a maximum, we have in the book that we have this little delta V. I don't know if I can write this. Little delta V is equal to big delta V. The point is, if you look on page 6, in my book it's page 694, we have this relationship I max sine 2 pi ft, which we're not really worried about the time right now, but this would be give you 90 degrees for an inductor. So you can see at the bottom of the page that we have these rules. Number 1, instantaneous voltage across resistor is in phase. Number 2, an instantaneous voltage across the inductor leads the current. So instantaneous voltage across an inductor leads the current by 90 degrees. So it's exactly out of phase. So then what we have is instantaneous voltage for a resistor is I max times R, which we found earlier, and that was, what was it? It was 130 volts. But because this is exactly 90 degrees out of phase for the inductor, it's going to be 0. And then for the source, we just sum all these up. Let's call that source is equal to, right, where I is equal to, I don't know, R, L, etc. So that gives you 130 volts. That's just the total. That's what I'm trying to say. You add these up, you get the total. It's 130 volts. Okay? So for part D is very similar. Part D is very similar. We have the instantaneous voltage across the resistor, where the current is 0 times the resistance. Well, that gives us 0, right? And so, because across an inductor we're 90 degrees out of phase, we're going to have a maximum, because we're exactly out of phase, right? So we're going to have a max, and the max is going to be, I think we actually already found it, didn't we? We did. It's 120 volts. So that's going to give us 120 volts. And so again, we sum these up for the source, and because we have 0 plus 120 is equal to 120 volts when the current is 0. Okay, that's how you do that. For further information, see page 694, 695 in chapter 21. Final problem, number 33, 21.33. We are given some RLC circuit as usual, where R is equal to 225 ohms. The inductive reactance is equal to 175 ohms. And we are asked to find, let me rewrite this, this doesn't look like an L. There we go. We are asked to find XC for, if we have a power factor is equal to cosine phi equals 0.707. And then we do the same thing. This is part A. We do the same thing for parts B and C. If our power factor of cosine phi is equal to 1, and 1 times 10 to the negative 2. Okay, so let's note that what we're given, right? This is the given RLC circuit. We have R, we have a value for R, and we have a value for X sub L. We also have values for cosine phi, which if we take the inverse cosine of this value, we'll end up with an angle, right? And so recall that we have this relationship XL minus XC over R is equal to tangent phi, right? We have R and XL. We can find a value for phi by taking the inverse cosine. So if we did this, phi is equal to cosine inverse of 0.707, then all of a sudden we have an angle, right? And so since we're solving for XC, we can plug this in here. So now we only have one unknown and one equation. That's totally fine. So let's solve for XC first. Let's do this. So let's see, what do we got? We have R times tangent phi, right? Minus XL is equal to negative XC, which gives us XC. Capacitive reactance is equal to inductive reactance minus R times tangent of phi. Okay, so all I did was solve for XC from this formula, and now we're going to take each value for A, B, and C, which we have here, A, B, and C, and then we're going to plug those in as our angle. So what that's going to look like, it's probably better to do it separately, but as an analytic way of looking at it, we can do something like this. So this would be part A. And that gives us a value. Let's see, what do we get? Negative 50.08. I'm not sure if that's right. Okay, so let's just try this for the rest of them and see if we get any reasonable values. Cosine inverse of 1. This actually goes to, this value goes to 0, and you're just left with 175 ohms, which is perfectly reasonable. And then that's part B, that's part A. Part C, we got XC is equal to XL minus R times tangent cosine inverse of, what did we had 0.001, which gives us a value of 11890.1 ohms. Sure, which gives us, say, 1.2, say, 12 kilo ohms about, right? that's how I went about solving it. I'm not sure what is reasonable in these situations, so if you have a better way of doing this, get in touch with me through Canvas or through sending me an email and let me know.